Okay, good morning. Good morning, everyone. Sawadee Kap. Welcome to mini workshop on sustainable energy and resources engineering. This is Tatsuya Mizukoshi, the director of Tokyo Tech, Annex, Bangkok. Okay, before starting, I will give you some notices. First, when you have questions, please write your question in Q&A on the Zoom toolbar. Be aware that it may not be possible to answer all questions due to time constraints. And about discussion, if you have any opinions or comments during the discussion period, please use the chat or please raise your hand. And this workshop will be recorded and will be opened later on NASDAQ and the Tokyo Tech website. And this is today's program. Then let me introduce today's chair, Dr. Pavina Parapainaina.
Yes.
Sorry, it's difficult to pronounce. So, Pavina-san, I will hand over the proceedings, so please go ahead.
Okay, thank you very much, Professor Mizukoshi. Okay, and welcome all the audience and also speakers. So today we will start the program by Professor Penjit Srinopakun, who is our first speaker for today. She's from Faculty of Engineering, Kasetsart University, and her topic today is Bio Lubricant from vegetable oils. Please welcome Ajahn Penjit Srinopakun.
Thank you very much. So I will share my slide. Good morning, everyone, and thank Ajahn Pavina very much for your introduction. And first of all, I would like to thank the organizer to invite me today to share our experience in biolubricant synthesis. So actually, when we're looking for the biolubricant, we have to mention about the base oil, because this is the most essential for the lubricant synthesis. So the base oil can be actually the vegetable oil, as you know that because it's like, I would like to mention about the properties of the base oil, which should be very high lubricity, polar nature, high viscosity index, and high fresh point. And of course, in our case, because we use biolubricants, we're looking for the properties of biodegradable and non-toxic. So after we have the base oil, we will add additive to make various types of the biolubricant. So as you can see here, I mean, the base oil usually made from the petroleum oil. Let me show you the comparison between the petroleum oil and the biolubricant. You may see here that in the petroleum oil, they are non-polar. So when it attached to the metal surface, it will be like this, like random and not a good one. But for the biolubricant, we have like more polar than the petroleum. Then you can see it here. When it attached to the surface, it will be nicer. So, but why we use lubricants? Because it helps us a lot in the heat and wear, and also save energy cost. So what about when we're thinking of like, we're gonna use the vegetable oil as the base oil? The question come up like, can we use it directly, immediately with our modification? The answer is no, we can't do that because the vegetable oil have poor oxidation stability, and it also poor, properties, not a good property at the low temperature. That's why we can't use the vegetable oil directly as the base oil. We need the modification, particularly in the structure of the triglyceride. So this is the structure, molecular structure of triglyceride. As we can see it here, it very easily to be hydrolyzed, to be at the carboxylic group, and also in the oxygen in the structure is not tolerant to the temperature. And most of the vegetable oil in the world, actually, they contains unsaturated fatty acid and unsaturated fatty acid. And as we know that at the double bond is very easy to be oxidized. It means that our vegetable oil won't be stable enough to be a biolubricant, particularly at the high temperature. So how to modify the structure of the triglyceride? So we try to get rid of the unwanted properties. For example, we would like our biolubricants to be like high viscosity, which means we have to make a long molecules. How we make a longer molecules? Very simple question is that we just add more some structure into your vegetable oil. But how to? It's like chemical synthesis that we have to open at the double bond. It's very easy to oxidize, and we have to open into the epoxidized ring. So we open this and add oxygen into the structure. And because this epoxidized is unstable, later on we can add molecules, smaller molecules or branches molecules into the structure. Okay, if we add the long chain into at the epoxidized epoxy ring, we will have the properties of the higher viscosity. But if we can add the more branches, molecules into vegetable oil, we can improve the power point. And also, we have to modify the molecules to have more flash point, because the most of the specification we're looking for like flash point is higher than 250 degrees Celsius. So this all about the structure or chemical modification we have to do on our triglyceride or vegetable oil. So in our study, we propose like, okay, in our study, we have objectives of the synthesize the biolubricant from the vegetable oil, and also investigate what properties we have after chemical modification. But in our literature, because as you can see that we need double bond in the molecules, that's why we're looking for the chattofa oil or soybean oil, because in those oils, they contain like high unsaturated fatty acid. And we go to the 5 step of the chemical modification. At first, we have to do the hydrolysis and separate. We separate out or remove the unsaturated fatty acid. We would like to have more unsaturated fatty acid. So step 1 and 2, we will have a lot of unsaturated fatty acid. After that, we come to the step 3, make epoxy ring at the point of the double bond. So we have to do that. And then we will do the real modification by adding whatever molecules we think is good. In this case, we would like to improve the viscosity. That's why we use like palm fatty acid, because it's a long molecules containing about the 16 or 18 carbons. And we expect that it will increase the viscosity. And after that, we would like to improve the flash point and the power point. So we will do the last step of the reaction of the esterification, because like after the epoxy ring opening, you can see that this is contained OH group. It's still unstable. We would like to have the bio lubricant which have more stable and also like maybe increase other properties. So that's why we do the last step. So at the end, this bio lubricant will be the ester, but with a lot of detail in chemical structure modification. Okay, so let me go to one by one of this modification. At first, we do the hydrolysis, and of course, we success to increase the unsaturated portion in the vegetable oils. For example, in the Jatropha oil, we used to have like this is we cut the molecule first into fatty acid, and then at the beginning they have like 5% of fatty acid, then we can increase to 99%, as well as like soybean. We bought it from the department store, from the supermarket, so the fatty acid is very low, undetectable, about 0, and then we have fatty acid into 99%, 99.75, and after this we separate now. We would like to have only unsaturated for the further reaction. So in this case, at the starting, we have about like unsaturated about 79%, and after this reaction, we can increase it into 97%, almost 98% in Jatropha oil. And from the soybean oil, we can increase like from 84.14 to 99, almost 100%. So the important number one here is the yield. But the yield, you can see at the moment, we can do about 60%. We try to improve it later. So let me show you about the composition of the fatty acid of both oil. If you're familiar with it, you can see that like this is unsaturated, increased like 48 to 53, and this increase slightly increased. But you can see 18.2 increased quite a lot, which is very satisfied because we need to go to modify at the unsaturated position. That's why we would like to have happy. We are happy to have 18.2. Okay, now it's time to open the ring and make the epoxy. So when we do the reaction, it's very difficult to notice the physical properties because look the same. I mean, that's why we need like NMR to check the structure of the molecules, whether or not we did it like successfully. So we used NMR and we have like some calculation. The position we look at like 5.3, this is show double bond, and this point have to change into like 2.9 and 3.1. So this is a key of the analysis that we're looking for. So I won't go to the detail of the peak, but if you have questions, you can ask me later. But there we check at the position as I mentioned before. And it shows that we have a good modification in the molecule. Yeah, so, and we can, sorry, I should show you the successful, the percentage of changing is 94 for Petroleum Oil and also 95% for the soybean. We have like quite certified for this one. And the next step, we do the epoxy ring opening. This is very important because after you have the epoxy ring, now it gives you a chance to modify the molecular structure. So again, we need NMR to help us to show whether or not we did it or we successful or not. So in this case, it showed that the peak look different pattern. I mean, without knowing which ppm, you can tell that it changed the structure quite a lot. Here, we check whether or not it's the same. So the hydroxy group still unreacted. This is very important why we have to check this point, because we will do the other reaction of esterification later. So we don't want this hydroxy group change. We would like it to remain until we finish this reaction. And you can tell that we are quite successful to have this remain. And here we check. This is important whether or not we can add the PFAD into this position, and we are successful also. Good. This is Petroleum Oil, and also we check not only like we add the PFAD, okay, but it showed the disappearance of the epoxy ring of our product too. Okay, this is the color on the pictures of the biolubricant look like. So we have to vary the ratio of the PFAD because PFAD contain a lot of saturated fatty acid. If we use it in excess, the remaining PFAD can be our problem later, because PFAD will like a low power point. So we don't want that. That's why we have to, and as you can see here, if we add the high ratio of the PFAD, like 1:5:1, you can see that it's become like actually it becomes solid at the room temperature. We don't want that because the properties of the biolubricant is about like a power point of -15 degrees Celsius. That's why we have to vary the ratios of the PFAD and epoxidized fatty acid. And we found that for the Petroleum Oil, maybe 0.9 to 1 or 1 to 1 is the a good condition. Different, I mean, a little bit different from soybean. You can see that 121 is certified and quite a clear but dark brown color. So it's clear here. You can see that 1.121 for soybean. You can see like it's become solid on the surface. Not good. We don't want that. Okay, so now we come to the last step of the molecular modification. In this case, we're thinking of what kind of alcohol we should use for this modification. In our case, we use ethyl hexanol because like if we use just methanol, actually is the cheapest, but we afraid the length of the molecule won't long enough. That's why we're looking for the higher carbon number alcohol, but not too expensive, of course. Okay, finally, we have our biolubricant on this one. We have two different one, like we have like two different one, like the Chattophar and soybean, and we have truffle equation a bit, reaction a bit. That's why we have two formula. So this one like is like ester of epoxide ring opening product, but this one we go to the ester directly, not opening ring first. So we try both steps. So this step to the end that I explained, it's shown on this table that we have a very good properties as well. And actually, without any modification or adding any additive, it's only meet the requirement of ISO VG 32. So this is very good without adding additive. We get biolubricant under this like category. You can see here many categories for the biolubricant depending on the application. But if we don't, we just use like step 4 and 5 together. This one we put together, not separate into 1, 2, 3, 4, 5, but we did 1, 2, 3, 4, 5 together. So we have a different kind of the biolubricant. In this case, the viscosity become problem for the Chattophar oil. So this one can go to this like can be ISO VG 100 or ISO VG 150. So this one, you can see that the viscosity is a little bit over. So the next step, I think we should cut the molecules to make a shorter molecule and reduce the viscosity. But for the soybean, it seems that we fit this ISO VG 150. So yeah, but of course I have to mention that we need very exactly analysis, because like we have to go to the standard lab and check every parameter again before we can transfer the technology to the company. Okay. Oh, French boy. Oh, still problem, because in these two category we need like 205 and 225. So we still have need further investigation on this one. So at the end, I would like to conclude that we are successful to develop the biolubricant suitable for ISO VG 32, which can be the application for the hydraulic pump, industrial gear oil, and hydraulic machine on the farm or forest. So, but another specification we need further study. So we success to modify the viscosity, decrease the power point, and increase the flash point. And this is the information I obtained from the paper published last year. If you need more information, you can go to the papers. I would like to thank the organizer to give me a chance this morning to share our experience on biolubricant synthesis. And also I would like to thank our department chemical engineering at Kasetsart University and our sponsor for the chemical and also the student scholarship. Thank you very much. Thank you.
Okay, thank you very much, Dr. Penjit, for a very good talk. Okay, so we'll keep on to the next speaker, Associate Professor Ryuichi Ekichira from School of Environment and Society from Tokyo Institute of Technology. His talk is Biorefinery Production of Biodiesel Fuels. Please welcome Ekachira Sensei.
Okay, Sawadee Krap. Thank you for your introduction, Chairman. Ekachira Krap. One year I will talk about the biorefinery production of biodiesel fuel. These are the contents. Just a moment. These are the contents. First, I will briefly outline the biodiesel production process. And the second is engineering technique to improve reaction operations in process. And the third is efficient utilization of byproducts in the process. These two, section 2 and 3 are the respective subtopics in the biodiesel fuel study in our research group. Okay, but my talk maybe will be very rough, which please note, and respective contents in respective section shown also here. Okay. Okay, just a moment. Okay, first I will talk about the outline of the biodiesel fuel production process. Before that, briefly mention the biorefinery. According to the IEA bioenergy definition, the biorefining is the sustainable processing of biomass into a spectrum of marketable bio-based products and bioenergy. In this bioenergy, the biodiesel is included. Okay. Next, I will outline the biodiesel production process. First, we should select raw materials, for example, waste oil, used frying oil, and so on, plant oil, and so on. And this is followed by these operations. I will use this flow sheet, process flow, to explain. The feed biomass, from feed biomass, we recover the feed oil. This feed oil contains many unfavorable impurities, such as free fatty acid, phosphorus component, and water. So we should pre-treat this oil beforehand to provide this to the main reaction, trans-esterification, or into the biodiesel fuel. And this biodiesel from the trans-esterification reactor also contains many impurities. So this should be purified into the final product, biodiesel. And also in this process, we several byproducts discharge or flow out. For example, solid residue from the oil recovery and crude glycerol from the trans-esterification. So we need to use these byproducts appropriately. And in this presentation, I will show the study using Jatropha oil, which is also mentioned in the previous study talk by Achan Penjit. And the Jatropha contains, in general, highly toxic compounds, so inedible. So this is not conflicted with food use. And also, Jatropha grows very well, even in harsh condition like aridity or very sterile soil. Okay. Okay, next, let's get into the respective topic. First is engineering technique to improve reaction operations in the process. That is reaction equilibrium rate and multi-stage operation. This is just the same flow sheet as the previous slide. This section, the reaction operation in this section is this pretreatment and the trans-esterification. Here, in pretreatment, we studied only this FFA removal. By this FFA removal, phosphorus, a certain amount of phosphorus can be removed, and also separate the water. Okay. I mean, here, by the laboratory scale experiments, we obtained these kind of parameters. And by using these parameters, we simulate these reaction operations computationally to improve the process. Okay. First, I will talk about the estimation parameters in reaction operations. This figure shows the experimental laboratory batch reactor, which we use to obtain the parameters. This is a very small, about 6 centimeter in diameter, small stirred vessel with a buffer and stirrer. Okay, and first, I will talk about the FFA removal by esterification. There are two methods to remove FFA. One is a neutralization, the other is a esterification. But usually, almost all of the studies about the FFA removal are conducted using neutralization because the reaction rate is very high. Instead, the esterification method give a relatively low reaction rate. So we need many amount of reactant. But these figures compares these two FFA method. This is the yield of oil in this treatment, and this is the final FFA concentration after the treatment. The oil yield in the esterification method is higher than that in the neutralization method, and performance to remove FFA is almost the same. So we focus on this this difference between among the yield. So we use esterification method. Okay. For example, this CJO means crude jet power oil. This is concentration, initial concentration of FFA in crude jet power oil. These are presented. Okay, next. These are the basic reaction on the reaction rate and the mass transfer rate related to the FFA removal by esterification. Okay, and using these relations, we obtained measured parameters together with these experimental results. This is a time course of concentration in FFA removal by esterification experiment in FFA removal by esterification. And using these experimental results together with previous relationships, we can obtain these parameters, equilibrium constants and reaction rate constant. Okay. Next, let's get into the trans-esterification operation. In here, we use very general alkali catalyst method. Similarly, this operation can be represented by these reactions and rate equations and mass transfer equations. And also similarly, we can obtain the parameters in this operation or using previous equation and this kind of experimental results in a batch reaction. And in this case, we also correlate the parameters with temperature using this Arrhenius equation. This is also very ordinary equation, not so special one. And by this correlation, we can obtain, this one, activation energy. And furthermore, we correlate this activation energy with this empirical equation like this. So finally, we obtain the relations among parameters and operating conditions such as temperature and concentration of catalyst, NSOH. Okay. Next, I will talk about the computational simulation of multi-stage reaction operations with obtained parameters. This is a brief schematic diagram of continuous countercurrent multi-stage operation. You can easily understand. This is a 2 stages, for example. Very simple. The oil is flowed from left to right in this figure, and the methanol phase flows from right to left. And these are the reactors. Okay. And in the case of FFA removal by esterification, these are also the relation and the equations related to the FFA removal by esterification, but these are written for the continuous operation. And using these equations with measured obtained parameters, we can obtain these results. This black line shows the result with a single stage operation. And these red lines shows the multi-stage operation. Here are only 2 stages. By only doubling the number of stages, 1 to 2, the amount of the required amount of methanol could be reduced favorably, like this. And next, I will talk about the trans-esterification part. Similarly, we use these equations. These are for the trans-esterification in continuous operation. This is the reaction and the material balance and the reaction rate. And this is a result obtained by solving previous equations with obtained parameters. And this black line shows the single stage operation. And these red lines shows the 2-stage operation. Also here, by doubling the number of stages, we could reduce the amount of methanol, and we can lower the operating temperature for required for the reaction. Okay, so and finally we compare these results with existing process. These are just the same. Black line shows the result with single stage, and the red ones shows the result with double stage. And sorry, this dashed line shows the existing process result. The ordinate is the required amount of methanol. By using the double stage, we can obtain the result which is lower than existing process. Existing process means FFA removal with neutralization and trans-esterification. And almost the same or lower. And furthermore, we can obtain higher yield in FFA removal by esterification. So we could obtain relatively good results. And so finally, if we summarize proposed process like this, this part is here feed crude oil, crude jet oil, and this is a 2-stage FFA removal by esterification, and also this is a 2-stage trans-esterification. So we can obtain biodiesel fuel with neutral, kind of a washing of crude jet oil by glycerol, and washing by water, washing the biodiesel, crude biodiesel by water. And these methanol, unreacted methanols are appropriately recycled like this. Okay. Next, I will talk. Next, let's get into the next subtopic. The efficient utilization of byproduct, purification of glycerol by adsorption using activated carbon derived from biomass waste. As I said, we obtained several byproducts from the process. So we studied about these effective utilization of these byproducts. Mainly, we are trying to obtain pure glycerol, which can be used for the food, pharmaceutical, and the cosmetics. And in the previous study, various kinds of purification method, but these are relatively high cost method. So here we try to apply solvent extraction and adsorption using Jatropha shell activated carbon. This Jatropha shell is one of the waste in the process. So by this, we would like to avoid the harsh condition and try to use waste byproduct efficiently. The first is that this is a solvent extraction of crude oil to remove fatty acids. I show only results. Here we use the heptane as a solvent to extract the fatty acid. This figure shows the fractional yield of the fatty acid from the crude glycerol. We obtained about 80 to 99% of the yield. So we can present the possibility to remove fatty acid by extraction with using the hydrocarbon. And the next is adsorption of crude glycerol using Jatropha shell activated carbon to remove colored compounds. The first, we prepare the activated carbon from the Jatropha shell, and we obtain the activated carbon, which characteristics are like this. Next, we use this activated carbon to remove colored compound in crude glycerol. Here, we used glutamic acid as a kind of a model of a colored compound. But the reason of this is very complicated, and it takes very long time. So sorry, but I omitted the reason why we select this one. So also in this case, we can remove this glutamic acid by this adsorption using this Jatropha shell activated carbon by batch equilibrium adsorption. The fractional removal is about 20 to 50% at maximum. So we propose this process. This is a biodiesel production with this is a biodiesel production process. Now, from here, we obtain the jet roller shell and the crude glycerol. This crude glycerol first treated by solvent extraction. After that, treated by adsorption. At that time, we use activated carbon or prepared from the this waste jet roller shell. So, and we can obtain purified glycerol. That's it. And also now we are considering these related plans, removal and recovery of toxic compounds in jet oil, removal of other impurities in crude glycerol, and the biodiesel production process using other raw oils, and also this is just the beginning, but the oil extraction from spent, Doitun coffee ground. That's all. Copy markup.
Okay, thank you very much, Professor Ekashira. Now, next speaker will be Associate Professor Pakorn Opapakasit from School of Biochemical Engineering and Technology, Siddhinton International Institute of Technology, Thammasat University. The topic of the talk is bio-based functional materials in water treatments and purification. Now let's welcome Ajahn Pakorn, please.
Thank you very much, and Pavina, for your kind introduction. So please let me share my slide. So does it show up correctly?
Yes, it is.
Okay,ครับ. So I will share the progress of our work on the bio-based functional materials, especially for use in water treatment and purifications. So I'm from SIT Thammasat University, and also from the Center of Excellence in Functional Advanced Materials Engineering, or we call in short COE FAME. I will share some example of the materials that we develop at our research center, right, related on magnetic nanoparticle containing materials, right, in the first two topics here. And after that, I will go into some detail of bio-based material that are used as anti-scalants in water cooling system, and also some example of our chitosan-based materials that are applied as a composite membrane for water filtration. So in our research center, COE FAME, right, we have conducted the development of materials, right, starting from synthesis, right, especially materials that are from bio-based or bio-inspired materials, right. After synthesis and characterization, we also do computational analysis and design, right, in order to apply our materials, right, into products. Right. We also develop material processing or manufacturing and testing for our developed materials, especially using 3D printing or electrospinning. Right. And also a separate part of our work also focus on the use of microwave and plasma technology in enhancement of materials properties, right? And also the use of this technology in converting or chemical recycling of plastic materials, right, into new value-added products, right? we also have done some work on the development of an analysis devices and sensor, especially for chemical sensor as well. So the first example of material that we develop and I would like to share with everyone today is magnetic materials, right, that we call magnetic framework composite or MFC. Right? So we develop magnetic nanoparticles and then we coated the surface of these magnetic nanoparticles by MOF or metal organic framework. Right? So this can be used in various applications, and the properties of this material, right? Some unique property will be the ability to be separated by magnetic field, and also the ability to specifically absorb or decontaminate many pollutant in water system, and also the ability to be heated, right, by using induction heating and to regenerate the material. So the material can be reused for more than one cycles. So the example here, right, we develop magnetic nanoparticles that are coated by particles or sheet of a MOF that is called mu-53 aluminum. Right? So mu-53 aluminum has very good absorbability, and the magnetic core, right, provide the magnetic separation ability and also the hyperthermia properties that we can heat the material in a rapid time, right, in a short period of time, so we can regenerate the materials. So these are SEM and also TM picture of the material that we have developed, and we apply, right, these materials into the decontamination of various antibiotic drugs that are contaminated in water system. And the example that I show here is on the treatment of oxytetracycline or OTC, which is one of important antibiotic contaminant in water. And we study the absorption mechanism and also the absorbability of these materials, right, as a function of pH, right, because we know that the structure of this drug, right, have different type of charge. So their structure is strongly dependent on pH of the system, right? And we can see that the absorption capacity of the materials, right, also depends on pH, right? So the highest absorption capacity can be obtained at pH around 8 to 10, right? And after that, we see the decomposition of the material when a very extreme pH condition are applied, right? So, and we, according to this, we also can explain, right, the mechanism, right, the structural change as a function of temperature of the materials, right? And also the interaction that involved with this absorption of the drug. And we measure the absorption isotherms and the kinetics model, right, to explain the absorption capacity and also absorption ability of these materials, right? So we found that the maximum absorption capacity, right, of the OTC, right, is around 800 milligram per gram of the materials, right, which is quite high. So the overall application of this material, right, we can apply the material to absorb the contaminant species and then use magnetic field in order to concentrate the materials, right? After that, when we concentrate the materials, we can regenerate the materials, right, by using induction heating, right? to heat the magnetic core inside the materials, right? So this can make local temperature on the magnetic particle very, very high, but the temperature of the surrounding water, right, can be up to 70 degrees Celsius, right, for only around less than 5 minutes of heating, right? And after regeneration, we can reuse the material, right, in the absorption or the decontamination process, right? We can see that up to around 5 cycles, right, the absorption capacity is still very high, and then will be lower after those cycle. So that is one part. Another part of the work that I want to share here is on anti-scalant chemicals, right, which are very important chemicals used in water cooling system, right, to prevent scale formation in the system, right? So the volume and also the market size of this type of chemicals is very high. And in general, right, the commercially available anti-scalant on the market can be classified into 3 or 4 classes, right? Polycarboxylate group, phosphonate group, and polyphosphate groups, right? So these are 3 common anti-scalant that are used, especially in water cooling system for electricity generating plants. So, if you look at this structure, right, these chemicals are fossil-based and also can be harmful to the environment, right, after discharging into the water system. And so we develop a process of producing material that contain magnetic nanoparticles, right, in order to trap these materials, right, or regenerate this material, right, after use them as anti-scalant in water cooling system. So by doing this, we can lower the amount of anti-scalant that are discharged into the water resources, and also to enhance the capacity of the materials, right? And if we can use the polymer that are from bio-based and can be degraded at the end, the material can be very, very friendly to the environment, right? We start with the first system here. We make, we synthesize copolymer of polystyrene and acrylic acid and apply this, right, to coated magnetic nanoparticles, right? So we have the material that can that have acid group here that can absorb cation that are in water system, right, but can be separated by magnetic field, external magnetic field, right? So after the synthesis, we vary all parameter to optimize the properties of the materials, right? So we look at the magnetic content of the materials. We look at the colloidal stability of the materials, right? So to make sure that they can disperse in the water very well. We also measure the magnetic properties, right? So the material show super paramagnetic properties. After that, we test the performance, the absorption ability of these materials, right? So various type of metal, ion, right, have been employed, and I show here is calcium ion, right, which is the main cause of scale formation, right? So we can see that the material show very good calcium absorption capacity, and also can be regenerated in up to 4 or 5 cycles with still very high absorption capacity, right? So from this result, we also test the anti-scale or scale inhibition efficiency of the material, right, in comparison with anti-scalant that are used commercially, for example, PBTC, PMA, or Akumer. So our material show comparable inhibition efficiency. Right? On top of that, we also study the prevention or inhibition mechanism. We look at the morphology of the materials, right? And also try to identify the mechanism of this inhibition. So as I said, actually this system, right, the polymer is still non-degradable after use. Right? So this may not be the ultimate solution. So if we can change the polymer that can prevent scale formation and use bio-based material, this should be very promising. So we therefore investigate the feasibility of using chitosan, right, as an anti-scalant. We know that chitosan are usually bio-based material that come from crustaceans shell, like shrimp or crab, for example. So in a nature form, this is in the form of chitin, and we can change this into chitosan by deacetylation reaction, right? But we can also modify structure of chitosan in many ways, right? And one of the promising way is by protonization or incorporation of positive charge, right, into the structure of chitosan. And this can make chitosan water soluble, and therefore this can be suitable for anti-scalant applications. On top of that, we also develop oxidation process, right, that are friendly to the environment. In normal oxidation process, we usually use various type of oxidant, right, especially those containing halogen groups, right, which can be not friendly to the environment, right? So we, in our center, we develop a process that is halogen-free, like using TEMPO and ozone, that can have like high efficiency in oxidation process. So we apply this, right, into the structure of chitosan. Therefore, right, we can make chitosan that contain protonized ion, right, positive charge. And at the same time, we oxidize this chitosan. So we introduce acid group into the structure of chitosan. So this material, right, contain both positive and negative charge of carboxylate in the structure. Right? So we call this chitosan polyampholyte, right? So that are suitable for scale inhibition applications, right? So we also test the performance, right, the anti-scaling efficiency of these materials, right? So we call this CPA 1 and 2 here, with different composition of the positive and negative charge in the structure. We can see the inhibition efficiency of our material, right, even better than commercially available anti-scalant that are not degradable after use, right? Our chitosan material can be degradable and come from bio-based resources. We also study mechanism, morphology, right, of the inhibition as well. On top of that, this material also show antibacterial properties as well. So we can say that this can be a three-in-one materials, right? So because it can provide antibacterial properties. So in water cooling system, right, we can reduce the use of antibacterial drug. So by using only this material. In a separate part, right, we also develop chitosan as a composite membrane and apply them in water filtration, especially ultrafiltration. Right? In this system, we incorporate benzalkonium chloride or BKC, which is antibacterial, into chitosan, and also composite with carbon nanotube. We see very unique morphology or pore structure of the membrane, and the membrane show improvement in hydrophobicity and also mechanical properties, and show good antibacterial properties. And also we test the performance, the filtration performance in terms of water flux and also rejection percentage, right, using different type of standard water system. So those are, right, some example of the materials, right, that are from bio-based, and also we consider them as functional materials, right, and also their potential applications in water treatments and also water filtrations, right? So if you are interested and to find out in more detail about this work, right, you can also look at our recent publication that are related to these materials, right? And finally, I would like to also thank the granting agency who support us for making this work possible, and also our collaborators, the researcher, the students, right, who are the main person who make this work possible. And I thank everyone for your kind attention. Thank you very much.
Thank you very much for your fruitful talk, Dr. Pakorn. Okay, before next speaker, let me remind everyone again, if you have any questions or any comments, please fill that into Q&A toolbars on the Zoom. Okay, so next speaker, Associate Professor Chihiro Yoshimura from School of Environment and Society, Tokyo Institute of Technology. The topic of the talk is water treatment using nanocarbon material, recent progress and challenges. Please welcome Yoshimura Sensei.
Hello, everyone. Good morning and good afternoon. Can you hear me well?
Yes, yes, sir.
Yes, thank you for the introduction. So now let me share my screen. Yes, I hope you can see the slide.
Yes, we do.
Yeah, okay. First of all, recently I have a problem with my camera. Sometimes it freezes my computer, so let me allow to turn off my camera while I'm talking. Sorry about this. So the title here is Water Treatment Using Nanocarbon Materials, Recent Progress and Challenges. So in the previous presentations, we had already some discussion and then the report of the recent research about nanomaterial. And then here I would like to continue those topics with together with some recent progress in my group. We are focusing on the water environmental management and also water treatment, focusing on domestic wastewater treatment. So besides the material development, we also check how much applicability we have with those developed nanocarbon material. This is our focus. So this is the first slide showing you the major material we have been developing in the past decades, starting with the charcoal, activated carbon, zeolite, and so on. And then we have an excellent technology to prepare the nanomaterial, for example, graphene or nanotube, and so on. Yes. So first of our interest is efficiency together with the target material, right? How much, for example, absorption we can expect, or we show it as a absorption capacity or absorption rate. Or sometimes we have a degradation as well. And in addition to this efficiency, we have to think about the specificity of the reaction as well, and also cost. in order to apply the new material and method to the water treatment. And then this course should include, this is usually including the course when we dispose the material after the treatment, after the use, or sometimes we have some method to reuse or regenerate this material. So to come up with some application, in addition to in addition to check the efficiency, like how much absorption we can expect, we have to think about post-treatment as well, post-treatment process as well. Yes. Anyway, let me start with a very simple one. So based on the graphene material, we can prepare those specific material, including the fluorine and nanotube and stack graphene. So our first interest was how much we can simply absorb the organic pollutant by using those graphene families. So expected reaction here, absorption, and sometimes we can use the reaction of photocatalysis, basically oxidation. And then the process could be the separation, oxidation, and disinfection. Disinfection, this is the case when we apply nanomaterial to the microbial community, right? So this was published in 2017. Maybe this was first step in our group. So we try to kind of, at the time we dealt with how to treat or how to deal with the nanomaterial, because the nanomaterial itself, we need to remove from the water after treatment. So as we have some excellent presentation in a previous talk, we were thinking to use the magnetic property of the CNT, carbon nanotube at that time. And then we knew that the development of this magnetic CNT needs some preparation and synthesis, maybe together with iron oxide or other metals. And then this student just found out the simple method. Just instead of preparing the magnetic property on CNT, starting with a very pure CNT, he focused on the little bit lower grade of the CNT. It's usually called industrial grade of the carbon nanotube. And then this low quality means some of the tube contain metals. This metal is coming from the production phase. And then we knew that by applying a strong magnet, we can collect the magnetic CNT from the low grade CNT in the lab. This was the first step, and then maybe this should be cheaper instead of preparing a very pure magnetic CNT, although we have to check the applicability for actual water treatment. But this can be done with a low cost, and as long as you have a strong magnet, we can collect it maybe in 1 minute or 2 minutes. This kind of refining process in the lab. So this is the first report in the group showing the green and facile approach for enhancing inherent magnetic property of the carbon nanotube for water treatment application. Yes. And then after that, we are thinking not only the absorption, we like to have also degradation, because absorption, after the process of absorption, we have to dispose this material, or we have to clean up the surface of the CNT. So as you know, I think everyone knows now. So by using the titanium oxide, we can do the photocatalytic reaction. We can make this reaction, but only under the UV. Yes. And then maybe you're familiar to this one too, but together with, if you can combine TiO2 with the carbon material, we can make a photocatalytic reaction under visible light. this means if we bring this material to the outside, and then if you got the solar light, we can expect some photocatalysis. This is usually oxidation of the organic matter. And then in case of the application to the water treatment plant, the visible light is cheaper than UV. And also this photocatalytic reaction could be doing the kind of cleaning of the surface of the material. So together with the absorption property, if you have photocatalytic property in the material, this would be maybe a bit more sustainable. Yes. So one student in our group did some experiment using acid blue. So here we have some example of the combination of the carbon nanotube and TiO2 at the different mass rate. And then this is the graph on the left side show the absorption kinetics, and the right side, this graph is showing you the photocatalytic regulation part, just starting the time point 0. So both part in the dark condition, we had absorption, and then solar irradiation. We have absorption plus photocatalysis. So starting with the initial condition and concentration 1 here, and it's going down over time. So for each part of the absorption and photocatalysis, we apply the model. And for the photocatalytic part, we found the best degradation rate with the mass ratio 1:5 of the CNT to TiO2. This seems to be good. I mean, the best to remove the acid blue. Sorry, this is not acid blue. This was the case with the carbamazepine, one of the antibiotics. So in this way, we found out the best combination to perform the photocatalysis after the absorption process in a dark condition. And then he checked how much recycling we can make with the simple cleaning of the material, or maybe we can apply the UV for the regeneration part. And then this was the next outcome in this research. So after that, we are also thinking of specificity. Imagine that in a wastewater, let's say domestic wastewater contain a lot of organic matter. They are not only the pollutant, right? And then if we want to focus on the organic micropollutant like antibiotics and then other pharmaceuticals or some personal use material, then we need some specificity because we don't have to remove all, I mean, for example, natural organic matter from the water. So this was the next interest. This diagram is showing us the size spectrum of the material. Maybe you are familiar to this one. So starting with 1 nanometer to 10 micrometer. And then here from the smallest one, we have a metal ion synthetic organics and protein, natural organic matter, and some microbes. They are existing all together in the wastewater. And then the question is, which component we like to remove? And usually this study was focusing on the small one, like synthetic organics. This is basically artificial compound, and then this shows some toxicity in the membrane. And then instead of removing natural organic matter, for example, we like to focus on the synthetic organics. And then this information below show the size of the pore together with the surface area. Surface area, if you compare the carbon nanotube and activated carbon, it doesn't show a big difference. The range are basically overlap, but the pore structure are very different. CNT contain the mainly mesopore ranging from 2 to 15 nanometer. In contrast, the activated carbon. This is one of the conventional material, show a micropore as a major structure. So the complexity of the pore structure are very different. As you can guess, the CNT showed a very simple structure. This is why we have some more space between the material. And in this case, if you check the 50 nanometer on the scale, then this comes somewhere here. So the range is from somewhere here to here. So if you want to apply CNT for absorption in the domestic wastewater treatment, we have this adsorbed also protein and natural organic matter. So those processes reduce the efficiency in removing the synthetic organics. This is not something like we want to have it, because of natural organic matter, basically we don't need to remove. We can ask other process to reduce concentration. Yes. And then like 1 milligram or 5 milligram carbon per liter would be okay to have it to release the water to environment. Yes. So this was our question, and then we checked different type of natural organic matter to see the absorption property in this case. So by combining the excitation emission matrix and also high performance size exclusion chromatography, and together, I mean, having a different type. I think at that time we tested more than 5 different international standard natural organic matter, which we have some information for. And this slide is showing a kind of conclusion, or this is actually the graphical abstract. So we have on the surface of the carbon nanotube, we found out non-preferable fraction and then preferable fraction. This means the mainly preferable fraction here in the relatively large molecules preferable show the preferable absorption on the surface of the CNT, but CNT was not very good at removing or absorbing the small molecule, which is less than 0.4 kilodalton, including microbial derived organic matter. So most of the large organic matter, usually including fulvic acid, humic acid, they are very good to be removed on the surface of the CNT. This means if you have a humic acid and fulvic acid together with a micropollutant, then the removal of micropollutant would be reduced. We have some interference by the natural organic matter. And then we confirm with this process with the experiment, and then preparing by the mixture with the natural organic matter and organic pollutant, we test how much we can remove. And so this, where should I start? The overall performance is indicated in this panel. So the x-axis is show the energy consumption. So the small energy consumption indicate better efficiency. So the upper part is without NOM and lower part with the NOM. So generally, overall, we see higher energy consumption when we have a NOM compared to the upper part. But still, if you combine CNT or magnetic CNT and TiO2, this is much better than having a TiO2 or only photolysis without the material. And then the difference in the color indicate the performance for the different type of organic matter, organic pollutant. And we've also find out the mechanism here of the inhibition, and the options are here. We had also we had a competitive absorption between organic pollutant and NOM. Second, reactive oxygen species scavenging process, and also inner filter effect on the light. And then from the experimental data, we recognize that the consumption of the ROS was the dominant process of the inhibition. Right? So this is the understanding, and we have to bring this knowledge into the application as well. So currently we are focusing on this issue, how to avoid this interference. We have to accept the natural organic matter to some degree. So some keyword here I just listed, starting with the hydrophobicity, side screening, and selective absorption. Selective absorption is a maybe common word in this research field, but we also try to see the hydrophobicity, the material hydrophobicity is showing some effective preferable process in the treatment of the organic matter or not, and also focusing on the size difference between a synthesized organics and natural organic matter. Maybe we can do size screening before coming to the absorption or photocatalytic process. And then recently we are doing this part of the experiment in the lab. And this is the review from our group. And then for future, we are thinking to apply it to design the kind of module which can be applied to the as an advanced water treatment process together with a conventional one. Right? So in order to make a module, we have to think about how we give the light, what kind of light we give, and how we design the pathway of the light, and then how much chance or how much surface area we have to give, and so on. This is a bit challenging still, but I think we have to come to this design in order to make use of it. Yes. And then maybe this is the last slide in my part. This one is showing the photolysis in a natural water body. So going out from the artificial system or wastewater treatment, we have also major interest in understanding the natural photolysis process in a natural water environment, because we believe this is also important to remove the organic pollutant where we have the light, sunlight in this case. And then under the sunlight, we know that we have a direct photolysis and also indirect photolysis. Direct photolysis is very simple as long as we know the light intensity, energy, and then the material or chemical structure, we can check the direct degradation. But for the indirect photolysis, this is a bit complicated because we have a kind of involvement of the reactive intermediate. Those radicals are coming into the reactions. And then those production and then reaction, the yield of the reaction depends on the source of the intermediate and also production of the intermediate. Yes. So it's a bit complicated, but I think it's worth understanding how much degradation we have. And then this degradation rate depends on the reactive intermediate production. And then together with the microbial degradation, somehow we have to quantify how much photodegradation we have in the natural environment too, in order to make kind of proper control of the organic pollutant. So with this keyword, we are trying to collect the natural water, doing experiment in the lab to come up with some finding some pattern or making a model to predict this direct and indirect photolysis process. Yes. So with this, I would like to finish my part. I'm not sure, maybe I talk too much. Sorry about this, but I hope we can have some continuous discussion with this. Thank you very much for attention.
Okay. Thank you very much, Professor. That was very good talk. Okay, so the last speaker for today. Thank you. The last speaker for today, Dr. Kachansat Phương Nawakit. Okay, he's from National Nanotechnology Center on NSTDA. The topic he's talking today is decarbonization, biofuel, biochemicals, biomaterials, carbon capture and utilization. Please welcome Dr. Kachansat. We cannot hear you. Maybe the microphone.
Thank you. Can you hear me?
Yes. No.
And the slide is clear?
It's
Yes, we
very
can
good.
now. Yeah.
Okay. Thank you, Chairman, for your kind introduction. So my talk today will be on the decarbonization approach, which is we believe that very important for tackling the climate change crisis in the moment. Okay, so in 2020, so around 30 or 40 gigatons of CO2 is released to the environment. So I think you know that, and it caused the climate change, climate crisis around the world. There are numbers of disasters that attacks us, everyone. And according to the Paris Climate Agreement, especially the COP26 just here last year, so we agree together that we need to suppress the temperature of the world. So so we have to reduce at least 1.5 or 2 degrees Celsius. Otherwise, we will go nowhere in the future. And the decarbonization approach is very important to do that job. And that will bring to the what we call low carbon society in the future, hopefully. And according to the McKinsey's report, they show the decarbonization strategies, which is divided into 4 major paths. And the first one here is the shifting to the renewable energy. The second one is decarbonizing industrial operations, and the third one, the forestry, and the fourth one is EV in short. And these 4 approaches are very important, and we think that if we combine with our R&D, so biorefinery and carbon capture, utilization, and storage seems to fit well with this 4 approach, especially as approach 1 and approach 2. And we believe that this approach align well with the BCG model of our country as well. And in my research group, nanocatalysis and molecular simulations, so we are specialists in the catalysis process. For example, thermocatalysis or electrochemical catalysis, photocatalysis, and this can be applied to different kind of production process of different biorefinery products or biofuels product or even material products. We believe that this align well with the SDG number 7, the clean energy, and number 13, climate action as well. And due to the time limit today, I will show you just some examples of the catalysis application in biofuel production, biochemical production, and CO2 reduction. Okay, because this is nanotechnology center, so we are quite good at synthesize or design nanomaterials, like for example, functional nanomaterials, nanoparticle materials, high precision catalysts, and single atom catalysts. So because we are the group of catalysis, so nanomaterials we produce are basically applied for catalysis application. You can see here we can synthesize metal oxides or metal sulfide, zeolite, organic frameworks, or nanocarbons like graphene or nanotubes, nanohorn, for example, and they're composite. And depends on the application we want to apply these materials to. And in the production process, when we apply our catalysis, actually we can produce a wide spectrum of chemicals and materials and biofuels. For example, we can start from biomass, and we can produce activated charcoals, for example, or graphenes, or cellulose nanofibers, cellulose nanocrystals. If we do more the reaction, we can convert the biomass into, derivatives of cellulose like sugars or sugar alcohols and some organic acid, for example. And in the hemicellulose pads as well, we can produce many kinds of chemicals. And if we start from the oily plants, which means that we may get the natural oils like triglycerides components, then we can also convert that oil into fuels like biojet or synthetic diesel or biodiesel, for example. Okay, for biofuel, the first part I would like to talk about today. Maybe around 10 years ago, we started work on the biodiesel productions. So I think many people here understand that biodiesel can be produced from waste oil or palm oil, animal fats, for example. If we put methanol in the reaction, we put the basic catalyst, we can get biodiesel and glycerol as a byproduct. And at that time, so even at the moment, the conventional process utilize the liquid catalyst or homogeneous catalyst. But our approach is that we want to replace these catalysts with solid catalysts. We call eco-cathode. With eco-cathode catalyst, the glycerin byproduct can be very high in purity, like 98 or 99%, which is far beyond the glycerin obtained from the homogeneous system. And we also can remove the washing unit and water removal unit. It means that we reduce the capital cost and operational cost as well. And there is no wastewater, which is the advantage of the eco-cathode system. So eco-cathode system catalyst is actually derived from the waste eggshells, which is produced from chicken farmings around the country. At the moment, I think more than 100,000 tons a year are produced in the countries. So we use the actually simple but effective thermochemical conversion process to transform the eggshell into a kind of nano sheet calcium-based calcium catalyst like these SEM pictures. So with the open sheet structures, we can produce trans-esterification effectively. And we start from TRL around 1 and 2, and we finish this work at the TRL, technology readiness level at around 7. We do the technical transfer, and we make the pilot plan and deliver this one into the industries, our industrial partners. And it's good that we can produce good quality of biodiesel past the national standard using our system. Now, people are talking more about better quality of biofuels. So there is one approach that can produce that kind of better quality of fuels compared to biodiesel. We call this system that deoxygenation process or hydrotreating process. Typically, we can start from the same thing, palm oil or waste oil, animal fat, but instead of methanol, we put hydrogen into the system. We change the catalyst type into something like methyl catalyst. And this is to remove oxygen from the structures of the fuels. Then we can get the hydrocarbon fuels, which is almost the same or very similar to the fossil diesel fuel. But of course, if we get better fuels, we have to use the condition which is a bit severe if compared with the trans-esterification process for biodiesel production. So we need high temperature and high pressure basically. And if we do a little bit cracking of the product, we also can get the biojet for the aviation application. So in our group, we developed the non-precious metal catalyst like cobalt or nickel catalyst to replace the palladium or platinum, precious metal catalyst, which is very expensive. Interestingly, we can get the high quality diesels. We call green diesel or BHD here, and we can get the high yield of the products. Actually, we can get the yield higher than 90%. Actually, which is very good compared to the palladium or platinum catalyst. And if we want to get the biojet, we need the cracking ability. So to produce biojet, we use different kind of catalysts. We use more metal phosphide catalyst, like molybdenum phosphide or iron phosphide, for example. And here again, we can get the product yield above 90% again. But what is promising here is that with iron phosphide catalyst, we can get the almost pure biojet fractions in our product. It is quite interesting results we get recently. With this work, we start from TRL around 102 as well, from the lab scale batch reactions around 10 or 1,000 milliliters per batch, and we develop the continuous system later on, and at the moment we do the IP licensing and tech transfer to the private sector to build up the pilot plan for testing in at the moment. So the TRL now is around 6. So we expect that we can move further for the real implementation in the near future. Okay, that is about the utilization of palm oil into the biofuels, but actually palm oil can be utilized in different applications. And recently, the country just announced the 6 strategic oleochemical products from the palm oil, like base oil, biolubes, biosurfactant, pesticide, insecticides, biotransformer oil, and paraffins. So you may be interested in this kind of R&D, and it is for your information. I want to skip a little bit into the biochemicals productions. This time, the feedstock for biochemical is not oil. So we basically start from the biomass, cellulosic biomass, with its further converted into a sugar platform, basically. One example I want to show you today is the production of lactic acid. So I understand that everyone know that lactic acid is the monomer for polylactic acid, PLA, one of the most important bioplastic nowadays. And the trends of PLA usage increase rapidly in recent years, actually, and it can be applicable in different fields. Okay, so lactic acid can be typically produced from sugars or glycerol, for example. But for sugars, so people use a bio process. The bio process actually very good. It can produce lactic acid with the high selectivity, but it's usually used long time, like 2 or 3 days. So here we try to propose the new way to produce lactic acid via the chemical catalytic conversions. So here it takes around 2 or 3 hours only. So, and let's see if it works well or not in the next slide. So here is our result. So we use different kind of acid catalysts like zeolite, alumina, and titania, and other things. And we found that this catalyst, it's especially alumina, works very well in selectively produce lactic acid from sugars. And it's clear that without catalyst, if you see the graph here, without catalyst, we will not get lactic acid at all. We get only furfurols, which is also the good chemicals for other application. So we proved that the solid catalysts play crucial roles in the lactic acid production from sugars. And in our group, we try to correlate the properties of the catalyst, like acidity of the catalyst, surface area, pore structures, for example, and the performance, I mean the yield, selectivity, and conversion of the catalyst to further improve the performance of our system. And at the moment, we actually have a new kind of catalyst just get published in ChemSysChem recently, which gives the super high activities of conversion and very high lactic acid yield. And also we do the optimization study in our group. Product purification is also essential for this process and the application of our chemicals. I think that the last topic of my talk today is about carbon capture and utilization, CCU in short. And so this is to utilize the carbon dioxide released from the factories. And people sometimes use the storage approach, and which is well, developed at the moment. So some company already use this technology to dump the carbon dioxide into the CO underground. The TRL level is very high, but for the utilization of carbon dioxide, there is still a gap, and the room to improve TRL at the moment is around 5. So many researchers around the world want to tackle these issues, the carbon dioxide utilization. And our group as well, focusing on the carbon capture and utilizations. So with the ecosystem in our group, we have the people doing the experiments, the simulations, and AI, and also the characterizations. So we can speed up the work on the carbon capture and utilization in our group. With the catalysis on the carbon capture and utilization, we can produce a number of products. At the moment, carbon 1 or carbon 2 atoms are the typical products from the carbon dioxide. So methane, methanol, formic acid, syngas, ethylene, ethanol, for example. And in the group, we also do the device engineering and computational and advanced characterization of this catalytic system. Here, I want to show you 3 reactions in the CCU process, which we are interested in. The first one is the CO2 reforming. So this reaction, we put CO2 and methane together. We put a high temperature, and we get the syngas, which is very important for industrial application. Syngas can be further converted into different kind of products. And our TIL at the moment is around 5. Another reaction is CO2 hydrogenation. So with this reaction, the temperature is comparatively low, around 200 or 300 degrees Celsius, and we get methanol. The reaction is not that difficult, but the thermodynamic limits the conversion. So they need some special tricky setup of the condition to push the conversion at high as possible. The TIL here now is around 5. And the last one of our interest reaction in our group is the CO2 reduction via the electrochemical process or photochemical process. So at the moment, we can produce ethylene from the carbon dioxide via the electrochemical process. And the TIL is around 4 in our group now. So still, we need much more improvement in this field. Okay, that is the reaction process, the production process we study in our group. Sometimes we can go to the pilot plant or the bigger size with the private sectors, but in many cases we need to we need the higher reactors, higher facilities, bigger facilities to scale up our system. So how to do that? If time allows, I will show you a little bit about the ECI which have the national scale-up facilities for the countries, especially the biopolis where I'm involving in. So that is the ECI is the facilities that important for scaling up of the process from the lab scale to the pilot scale. And in this pilot plant, we will have the GMP facility and non-GMP facilities working across different fields of biorefineries. And it is how the biorefineries pilot plant, I mean, ECI look like. Okay, and the biopolis, which is related to the biomass conversion, biofuel, biochemicals production, located here. And it is when under the constructions. And at the moment, the construction already complete. So we are now in the phase of detailed designs of the equipments inside each plant, and we hope that it will open for service in the near future, maybe in the next 2 years, for example. Okay, and this is the members from my group who work and provide the results for my presentation today. Okay, maybe that's all for my presentation today. Thank you.
Thank you very much, Dr. Kachansak, for your fruitful talk. Okay, now let me bring you to the next session, which is discussion for collaboration. Okay, so this session will be open for any discussion on this field.
Dr. Pavina, there are some questions in Q&A and also in
Yes.
chat.
Shall we bring the question? Okay. I'm not sure this question asked like the question based on chemical reaction in each step, how can evaluate the accuracy of the yield? Not sure this question is for which section?
I think from the timestamp should be for Dr. Kachansak maybe.
Yeah, from 1044.
Again, please, what is the question?
Can you see it from the Q&A question, Dr. Kachansak? So at the Q&A at the Q&A question, there are 2 questions for you, I think, from the timestamp.
Okay, so the question is about the yield. I'm not sure if which reaction, maybe the biofuel production. I think so. It's actually simple. So we analyze the composition of the product we get. So we know what is the composition in the final product, and we compare the yield by quantify the amount of the product and amount of the feed we use, and with the known composition, then we can, I think, calculate the yield. But if we want to know the yield of the intermediates during the reaction, maybe that is quite difficult. So basically, we during the reaction, if we want to know the yield of the intermediates as well, so we have to stop the reaction during the test, and with that process, we also can know the yield of each element during the reaction. I don't know if I answered the question or not. According to the CO2 reforming of methane, is this steam reforming or dry reforming? Dry reforming. It's dry reforming or CO2 reforming, not steam reforming. Okay. And I think in the chat panel, there is one question about eggshells. Which form I use for the catalyst. So after calcination, the calcium carbonate will be transformed into the calcium oxide. But calcium oxide is active for the transesterification, of course. But in our case, we treat it again by, for example, methanol or a kind of mixture of solvent. So sometimes we get the calcium methoxide, sometimes we get calcium hydroxide and other form, which is better for the transesterification reaction. I think that's all for me. So which catalyst type your lab are using? For dry reforming, I think because from the same from Dr. Itichai. For the dry reforming reactions, people basically use nickel cobalt or something like that. But dry reforming, it's the most important thing is the stability of the catalyst, because dry reforming can cause coking very fast, basically. So you need the good combination of the active sites and the support, which can suppress the coking rate. So that is the key of the dry reforming process. Okay, I think that's all for my questions. Thank you.
Yes, thank you very much. I think there's some more questions.
It's one question maybe for Dr. Penzit.
Yeah, the first question.
Industry usage condition, which type is better between jatropha vs soybean, supply and demand?
Yeah, I think like not much different. Actually, it depends on the percentage of unsaturated fatty acid. At the moment, we can get the yield is over 80% of the bio lubrication production. Yeah.
Okay. And another question is, have you ever used any other activated carbon from coconut shell for purification? Probably for Dr. Pakon, maybe for water treatment?
I think this is a question
Or
to
for
Dr. Egashira.
It's for Ikashira Sensei from
I
Thailand.
see.
Yes.
Okay, thank you. Thank you for your question. The question is, have you ever used other activated carbon from coconut shell for the purification? We have never used coconut shell activated carbon because this process based on the raw material of jatropha oil. So the efficient utilization of waste from the jatropha biomass is one of the purpose. And may that's it.
Okay.
Of course, if we use the coconut oil for biodiesel production, at the time, we might try to use the coconut shell activated carbon, but in my opinion, I think it's not so preferable to use the edible oil, like coconut oil or soybean oil, because purposes are conflicted. I think. This is related also the previous question for Achang Penjit.
For me too.
In this sense, the jatropha, in general, the jatropha oil is inedible because of the toxic compounds contents. So in this case, we don't need to care about the confliction with food use. But now I'm not sure about the amount of supply and demand balance of them. So also we can consider these points.
May I give more information about jatropha plants? Actually, it's non-edible, which is very good raw material for the commercial production. But I think at the moment we need a large scale plantation. And at Kasetsat University, we have a variety which have a high seed yield and high oil content. But because high investment, I think we need to look carefully about it. But for my biolubricant, we can produce it from any vegetable oils. Actually, as I mentioned, depends on the percentage of the unsaturated fatty acid in the oil. Okay. So for biodiesel, I think it's quite similar. You need 18.1, the merged portion, not 18.2 or 18.3. So because it involved the stability or oxidation stability of the biodiesel later on. So, but still, jatropha oil is still a good raw material for biodiesel production because it contains 18.2 less than soybean or sunflower oil. Yeah, thank you.
We have some
There are some questions to Dr. Yoshimura, but unfortunately he had an urgent business trip today, so he has already left. Sorry for that.
I think Yoshimura Sensei leave the email in on the chat screen. So if you have question, maybe you can directly contact him as well.
One question on what kind of polluted water to be treated, drinking water or industrial wastewater? Or why did you treat 15 minutes for the dark condition?
I think that's all for Yoshimura Sensei question, I think. But unfortunately, as mentioned earlier.
Even on carbon nanotube titanium oxide as well. Okay. So we still open for any more questions that you have previously. You can still ask me now. Or may I ask the question to Dr. Thenkit? Like, is biolubricants at the moment has been commercially used and compared with the petroleum lubricants? What's the situation at the moment?
Okay, thank you very much. Now we working with the private company to have like a formula, because there are many categories, and then we work closely with the company and to have a pilot plant, and hopefully soon we can commercialize it. Yeah, thank you.
Okay, thank you. I have still one more question for Professor Ikashira Sensei about the limitation of biodiesel production for industrial scale. Are there any limitation for production?
Limitation.
Or from lab scale is we can do it. You know, many researchers can do the biodiesel production, but going to industrial scale or commercialize, how hard or what the limitation of production?
When we started this topic, the main purpose is to use the main purpose to solve is the high cost of raw oil. So at that time, we try to use the used flying oil or jet oil or the like, or crude jet oil, not purified jet oil. So we are studying the pretreatment, but of course, it takes some cost for pretreatment. It's quite a difficult question. Maybe still a problem in expense for production. Now I'm not sure where is the controlling factor in the process.
Okay, thank you.
Okay.
Okay, then shall we move on to the introduction of a SERE project?
Okay, so the last before we closing, we have the session of Thai SERE program introduction by Professor Siripon Anantawaraskun, the SERE program director. Please welcome Ajahn Siripon.
Okay. So good morning, everyone. So my name is Siripon Anantawaraskun. I am currently a Thai side program director of the SERE program, and also currently a head of chemical engineering department at Kasetsart University. So first of all, I would like to thank Tokyo Tech Annex and also the mini workshop organizer for allowing me to briefly present the information about our Thai Tokyo Tech SERE program. And also thank you, Professor Pavina, for the kind introduction. So let me have pointer a little bit. Okay. So SERE program is an international and interdisciplinary Master of Engineering program in sustainable energy and resource engineering. This program is co-developed and co-operated by the National Science and Technology Development Agency of Thailand, or NASA, Tokyo Institute of Technology, Tokyo Tech, and 2 Thai universities, Kasetsart University and Silinthorn International Institute of Technology, SIT. At KU, there are 4 departments involved with the SERE program: Chemical Engineering Department, Environmental Engineering Department, Material Engineering Department, and the Environmental Technology and Management. Okay, so students registered in our program will receive a full tuition fee and also have the opportunity to receive the research assistantship, which covering all the living expense. Students can select 2 Thai university hosts based on the research topic that they are interested in. And students from both hosts, when graduate, will receive the certificate of attendance from the Tokyo Tech. In our curriculum, students from both hosts will register for the same core and elective course given by Tokyo Tech professor, KU and SIT professor as well. And then they will be able to choose a different elective course based on the host specialization. Students who graduate from KU, have the KU host, will eventually receive the Master of Engineering, Sustainable Energy and Resource Engineering from Kasetsart University. Those graduates from SAT will receive the Master of Engineering, Engineering Technology, Sustainable Energy and Environment. The student will also have the option, if they are interested, they can also register for more elective course and receive 1 more certificate on rail transportation provided by Mahidol University and Tokyo Tech. So the research interest in our SERE program cover several topics, and actually the speaker for today's mini workshop also involved with our SERE program. The research interest cover the green process engineering for sustainable development. This ranging from the process design, simulation, optimization, integration, and also process intensification. Waste utilization, converting waste to energy and waste to material. Environmental management and policy, this covering the environmental analysis too, like CT, LCA, eco-design, and footprint analysis. So development of the advanced material for the environment and energy, covering the bio-based material, biodegradable material, and eco-friendly material. Sustainable energy, this is also one of the very active area in our program, from alternative energy, solar energy, and battery technology. Also, we are interested in the biorefinery, which one of the main focus of the Thailand at the moment as well. Look at the biofuel and also consider the bioresources as the next generation of feedstock. And the research topic also involved the conventional waste treatment, wastewater treatment, air pollution control. And another topic is mainly on the climate change, like the greenhouse gases and the reduction and utilization and mitigation of the CO2, which I think from the speaker today, 5 speakers today also covering the research area that involved in our program. So that's briefly the information about the SERE program that organized by NASA, Tokyo Tech, and the KU and SIT. So if you are interested for more information in our program, you can access the following website, and also please do not hesitate to contact us by email if you have any additional query at all. So thank you very much for your kind attendance. ขอบคุณครับ
Thank you very much, Dr. Siripon, for a brief introduction of the program. Now let's bring everyone to the very last session of the mini workshop today. So it's the closing session by Professor Tatsuya Michikoshi. Please welcome again, please.
Thank you very much, Pavina Sensei, and all the speakers for today. Thank you very much. And about the inquiries, if you have any questions for today's workshop, and also if you have any questions to TAIST-Tokyo Tech program, please contact these addresses. You can speak Thai or English. And today's video will be opened later on NSTDA Tech website. Okay, then thank you very much for joining today, and see you again soon, maybe. Goodbye.
Thank you.
Thank you very
Bye.
much. Bye.
Thank you very much.
Thank you very much.
Thank you very
Thank
much.
you. Pavina Sensei, ขอบคุณครับ
ขอบคุณค่ะ. You're welcome. Thank you very much.